Okay, let's start the review while the rest of the class gets ready to go. So we had the last most important, one of the key things we did was the Gram-Schmidt process. So it's an algebraic means to start with y1 and systematically work up to yn and build an orthogonal basis. And so the key parts there is you start out with linearly independent vectors, you produce linearly independent vectors. The first k of the new vectors span the same subspace as the first k of the original vectors, and that's true for all k between 1 and n, but this basis is now orthogonal. If you want to make them orthonormal, you do one more step. Just divide by the norm. They have unit norm. We proved a result. Well, no, I let you do all the, we did the key step in a proof by induction. I let you by an exercise complete the fact that if you have any set of linearly independent vectors in a finite dimensional vector space, you can always find another set of vectors that complete it to a basis. And where we'll use this today is we're going to choose these in a special way. We don't kind of care how those happen, and that's going to help us out in doing one of our special proofs. We have the pre-projection theorem proved, and we're going to complete it to the full projection theorem today, and then we'll apply it and derive the result on A transpose A inverse A transpose B as solving a regression problem. The projection theorem, I'm changing the notation now to get ready for the fact that we're going to move into estimation problems, trying to find the best estimate of something given data. So it's a common notation. So the pre-projection theorem says given an inner product space, and we don't care about its dimension, given a subspace, and given a point in x, I can find, if there exists an x hat that is a best approximation, it's unique. So there's either one or none. If there is one, it is completely characterized by the fact that the error in your estimate is orthogonal to the subspace you're using to build the approximation. Okay, so using x hat to get ready for estimation problems. If we take any subset, does not have to be a subspace, we define its orthogonal complement by being all points in X that are orthogonal to every element of S. Since the zero vector is orthogonal to anything, this is not an empty set, not empty. And then by using the definition of span and the linearity of an inner product on the left or the right, you can show that the orthogonal complement of a set is the same as the orthogonal complement of its span. Consequence, not written here, if you know a basis for S and you compute the orthogonal complement for just the vectors in the basis, you've also computed the orthogonal complement for the subspace spanned by that basis. Okay? Right? Because that would be a subset, just a set of linearly independent vectors, and then their span would generate a subspace. Questions so far? 1, 2, 3, 4 questions? None, actually. Okay. We just wrote this down, and this is where we'll start today. So you have a vector space over the reals or the complexes and an inner product defined on it. And the key thing here now we're saying it's finite dimensional. So we have to see where we use the finite dimensionality. And our set now is not just a subset, it's a subspace. So we have a subspace of X. Then I can always decompose X into the vectors in M and those orthogonal to M. And remember, the direct sum means the intersection has to be the zero vector only. It's precisely the zero vector. Okay, so that's what it takes to have the direct part here. And we noted that was true because if X is in M and it's also in M perp, that means X is orthogonal to itself. So that means this inner product is zero, and the only vector that satisfies that is the zero vector by definition of something being an inner product. Okay, so the question we have, is it true that everything in X can be written as something in M plus something in M perp? We don't know that yet, okay? All we know is the only vector common to these two subspaces is the zero vector, but it could be that M plus M perp is smaller than X. Let's find out that it's not, okay? I will not take an enthusiasm poll just by looking at your faces, okay? I get it. I'm gonna just get to work. So, let's let K equal the dimension of M and N equal the dimension of X. If K equals N, okay, so in other words, if M is all of X, M perp is clearly just the zero vector and we're done, okay? So that's kind of a trivial case. So now assume K is strictly less than N. Well, we'll assume it's at least 1. I guess M could be the zero subspace, and then M perp would be all of X. That would be equally trivial. So let me write this where it's readable. Assume K is between 1 and N. And let Y1 to YK be a basis for M. Okay, so now what I want to do is using this information and the fact that X is finite dimensional, I want to actually compute the orthogonal complement of M. So how I'm going to do that, I'm going to use our result that says, given any set of linearly independent vectors, I can complete it to a basis for X. And that's where we're using finite dimensionality. So complete this to a basis Y1 to YK, YK plus 1 to YN for X. So we know we can do that. Okay, so now I want to compute the set of vectors that are orthogonal to M. What will happen if I apply Gram-Schmidt to this basis? I'll get another basis here that's orthogonal. I don't really care. But it still spans these first k vectors because Gram-Schmidt doesn't give me something outside of my subspace. And then I'll get a whole other set of vectors that are orthogonal to everything there. That sounds like M-perp, doesn't it? So that's what we do. Okay, so we apply Gram-Schmidt. To produce orthogonal vectors v1 to vn such that m equals the span of v1 to vk equals span of y1 to yk. Okay, so that's the key property of applying Gram-Schmidt, is that y1 spans same one as v, y1, y2 same as v1, v2, y up to yk, vk. Okay, so that takes care of the first part of these, but then these vectors are now all orthogonal to the others. Okay. And we have vk plus 1 all the way up to vn orthogonal to v1 to vk. Okay, so it's all done by Gram-Schmidt. From this, we have x equals the span of v1 to vk, sum span vk plus 1 to vn. This is m. These guys are orthogonal to m, so this is m perp. And so conclusion, x equals m plus m perp. And then because m intersected with m perp is the zero vector, we can put the circle here. Bingo. Okay, let you catch up. We'll do the highlights again. Take y1 to yk, we complete it to a basis, apply Gram-Schmidt, and we get, by construction, a set of vectors vk plus 1 to vn that are orthogonal to v1 to vk. Because this is a basis for x, x is the span of any collection of them plus the span of the rest of them. By construction, everything here is orthogonal to everything here. They're also orthogonal in here, but we just don't care. Okay, that's not useful to us. And then we'd already observed that this property is always true, no matter if it's finite dimensional or not. So bingo. X can always be decomposed as a subspace and the orthogonal complement of that subspace. Questions? Dubious, yes.
Those two subspaces have to be the same size.
Same size, same dimension, you mean? Well, if X is 37 dimensional and K is 4, then this is going to be 33. Yeah, because you start out with 4 vectors and you complete it to a basis for X. So you have to add dimension of X minus dimension of M vectors when you complete it. Yeah, so in general, they're very different in size. Because this, often in practice, this may be huge. It's really functions. This is a small set of them. Sine, cosine, sine 2t, cosine 2t, up to sine 5t, cosine 5t, okay? X is a whole bunch of functions, and we're just going to approximate our vector by a small number of sines and cosines. So, okay, so this actually completes the projection theorem. We'll write it down. The thing is, we don't know if this x hat exists. We know this is how we find it. So x minus x hat lives where? In M perp. It's orthogonal to M. So if I just write x as equal to a part in M and a part in M perp, because it's a direct sum, then this is the part in M perp, and the other part that's in M, we're done. Okay, so as long as x is finite dimensional and I can write it as M plus M perp, this thing is going to be very easy to find, such that the error vector, what's missing from x when you approximate it by x hat, the leftover, the error, that's in the orthogonal complement. But with x being M plus M perp, we're done. We're done. Okay, so projection theorem. We'll keep doing everything for the real, so we don't have to worry about the complex conjugate, etc. But let this be an inner product space, a finite dimensional inner product space. M contained in X, a subspace and little x just some point in X. Then, okay, so the only thing we're adding here is the finite dimensionality, and what that gives us is that everything in X is either something in M or something in the orthogonal complement of M, and that's what's going to do it, okay? Then there exists a unique X hat in M such that X hat equals arg min M in M norm of X minus M. Moreover, X hat is characterized by the approximation error is orthogonal to M. So, Okay, so what changed? Before we had if there exists an x hat such that then x hat is unique. That's what we said before. We didn't assert existence. Now we're saying then there always exists an x hat. It is unique. It's the argmin. Moreover, x hat is characterized by bingo. Okay, so question? No, the same thing goes for the complexes, just that I have to remember which side we're using to put the complex conjugate on if we swap the order, and I don't want to do that. Yep, so, okay, so the proof only thing left to show is the existence of x hat such that x minus x hat is orthogonal to M. That's the only thing that's changed from the pre-projection theorem. Okay. However, we know that x finite dimensional implies that I can write x as M direct sum, not transpose, orthogonal complement. Okay. Hence, there exists M in M and M tilde an element of M perp such that our little x is equal to M plus M tilde. Okay, so that's what's what it means that x is one subspace, sum another, everything in x can be written as something in here and plus something in here. From your homework, we could say there exists unique M and M tilde, but uniqueness we've already settled in the pre-projection theorem, so I'm not worried about uniqueness right now. All I know is I can write x like this. If I do that, x minus M equals M tilde is, gosh, that's really bad, is an element of the orthogonal complement. No wonder I'm leaning over like I'm much shorter than I am. Okay? Didn't improve, but anyways, hence x hat is equal to M. Okay? So x minus M is M tilde is in M perp. So we now know that x hat exists. I can take x hat equals to M when I write x is this. So as soon as I write x as something in M plus something in the orthogonal complement, I'm done. I've solved the minimum distance problem. So existence is actually super easy in finite dimensional spaces. Much harder in the infinite dimensional case. But okay. Okay, so just quick review once again. The only thing we had to show is that we could find an x hat satisfying it's in M perp. X equals M plus M perp, so I just write x as something in M and something in M perp. Then I'm done because x minus the thing in M is in M perp, and hence that thing is the solution. Bingo. What do you think? Clear? Elegant? Question?
What is this theorem, that projection theorem? Where is different from another theorem which we learned last section, lecture, or several sections? We also have a theory that calls x eta minus m0 and m in the subspace of x, and there exists a vector m0 for any x belongs to x. There is m0 is the nearest point to the x, and x minus x0 is perpendicular to n.
Oh, okay, so that's the pre-projection theorem. Okay, the question was about some of the previous work we had. And when we were proving the pre-projection theorem, the key thing we said was, suppose it's not orthogonal, then it cannot satisfy this. And so if x minus the m0 that we had, that's what we called it, is not orthogonal, we could find something in M whose inner product was not equal to 0. And then we built a vector that was such that x minus m in norm was bigger than the x minus the new vector. So that was part of our proof of the pre-projection theorem. Okay.
The previous theory was saying if this existed, then these properties.
Yeah.
This theorem is saying that it exists.
Yeah. So if I can find it, now we say if x is finite dimensional, existence is guaranteed. That's all we've added. Okay? Cool. So let's start putting stuff together. So we're going to do something called the normal equations. Okay. No for Rob, qual, exam. Okay, the normal equation. So here's the data that we're going to start out with. Oh, I don't want red. Come on. Be nice. X, R, finite dimensional. We're going to assume that we know a basis for M. Given x in x, seek an explicit formula for x hat. Okay? I just want to write down the answer, and it will be just as cool as saying A transpose A inverse A transpose B, okay? It'll be just as cool as that. And when we evaluate that formula for AX equals B over determined, we will derive the formula that I gave you from my 216 notes, okay? So this is where it all goes. Okay. So x hat is supposed to equal arg min m and n norm x minus m. Okay. So we know x minus x hat is orthogonal to m. So it's spanned by these basis vectors. So this is what m. We've got a finite representation of m. Okay. So one little exercise. Go back, come on, go back, yep. That's if and only if x minus x hat is orthogonal to yi, 1 less than I less than k. Okay, but if x minus x hat is orthogonal to m, this is certainly true, okay? Those are elements of m, but everything in m is a linear combination of these. So when I do a linear combination of things with zero inner product, I add up 0 and I get 0. So just write it down, and then that will be immediate. So now all I'm going to do is write down what orthogonal means. Okay, and then I'll use linearity to have this as x inner product with yi minus x hat inner product with yi equals 0. Whoops, if and only if 1 less than I less than k. So I use linearity on the left-hand side. And then for reasons that will be clear, I'm going to write this as x hat inner product with yi equals x inner product with yi. Okay, so all I've done is manipulate the statement x hat is characterized by the error is orthogonal to the subspace that we used for the approximation. Okay. So that gives us k formulas here that have to hold. I use the basis for m. Now, x hat is in m, so that means x hat equals alpha 1 times y1 plus alpha 2 times y2 plus alpha k times yk. Bingo. Oops. Okay, so let me just substitute in for this, and I'm going to get the I'm going to write down a matrix equation and a vector that involves these unknown coefficients, right? I want to find now these alphas such that this relationship holds, and then that will give me the optimizing approximating vector. Okay, it's a linear combination of things in M, and it's orthogonal. X minus x hat is orthogonal to everything in M, so that means this equality holds true. Okay, so this is the key formula. Inner product alpha 1 y1 alpha 2 y2 dot 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 alpha k yk with yi equals the inner product of x with yi. 1 I k. Question? No? Okay, so substituting in that x hat is in the span. Now, let's just write down what this gives us. Whoops. I equals 1, please. Okay, so we have linearity on the left. So far, everything works for the complexes, but I don't care, okay? So everything is fine here. So I have alpha 1, inner product of y1, whoops, I is 1. So this is y1, plus alpha 2, inner product with y2 with y1, plus dot, 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 alpha k, inner product yk with y1 equals inner product of x with y1. Okay, we'll do one more, and then we'll skip to the bottom. But so I'm just expanding this with I equals 1 and using linearity on the left-hand side. So I equals 2, we have alpha 1, inner product of y1 with y2, alpha 2, inner product with y2 with itself, dot, 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 alpha k, yk, inner product with y2 equals inner product of x with y2. So just brute force. We jump to the end, alpha 1, y1, inner product with yk, plus alpha 2, y2, inner product with yk, dot, 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 alpha k, inner product, yk with itself, equals x, inner product with yk. Okay, so barring typos, rightos, remember, these are in our field, so we're taking it to be the reals. The alphas are just real numbers. The inner product of our abstract vectors, those are just real numbers. Inner product of abstract vector x with our basis element, these are just real numbers. This is just a set of equations, simultaneous equations in alpha 1, alpha 2, alpha k. Okay? It's just a matrix equation. So let's just write it in matrix form. So you see? We've reduced this minimization problem to solving a set of simultaneous equations. It's just a matrix. It's totally, totally amazing. Okay, so now because we're doing the reals, if I take yi and yj and I flip the order, I don't have to care about doing a complex conjugate, okay? So that's the only reason we're doing the reals is just to keep ourselves sane when we're seeing this stuff for the first time. Okay, so surprise, surprise, I'm going to stack the alphas into a vector. But then I need a matrix that's multiplying them. What is that matrix? Okay, so this is what I'm going to define. This matrix, it depends on the vectors I use on the basis of M. its ij element is simply going to be the inner product of yi and yj. That's a j. Is this notation clear? What's the 1, 1 element of this matrix? Inner product of y1 with itself. What's the 7, 11 element of this matrix? The inner product of y7 with y11. Okay, so it's just a matrix. Now, it's actually symmetric because we're doing the reals. I can swap these orders. The matrix is symmetric. Okay. But this was a definition of the matrix. Alpha, I just stack them up. And I'm going to define another real vector, which is the element I'm trying to approximate, its inner product with the basis vectors. Okay, you guys got that? I want to switch back to the equations. Oh, beta. My brain had already jumped to the next symbol. I'm Turing incomplete, okay? I can't process all of my dots and dashes correctly. Thank you. Hopefully it's clear I was making fun of me and not you, okay? Does that really work cool? Okay, so that's just the notation. So now here's our simultaneous equations. So this is beta, that's real easy. We take alpha out, what's the matrix multiplying the alpha? G, okay? Now, technically, notice G21 is the inner product of Y2 and Y1, so it's technically G transpose, but G is symmetric, so it doesn't matter, okay? So I'll still write it as this, okay? G transpose alpha equals beta. And these are the normal equations. Equations, hey, squeezed in. Okay, so it's just a matrix form of our simultaneous equations. And if you write it as G alpha equals beta, I don't care, okay? It's totally correct because G is symmetric, okay? If you go back and you do the complex case, then this will help you a little bit when you're setting things up, but it doesn't really matter, okay? So know the normal equations for your qualifying exam. But the only thing I really want to point out is we've reduced this optimization problem to a set of simultaneous equations, and everything followed from our abstract characterization of what it meant to be a solution. It's orthogonal, and then knowing what a basis is, and using linear independence, et cetera, linear combinations. So all of our linear algebra, et cetera. The optimal solution is just this. And so x hat is alpha 1 y1 plus alpha k yk. Now, there's potentially one little problem we have to check. We want to solve G transpose alpha equals beta. This is just a k by k matrix, okay? What do we need to hold true for there to exist a solution? Invertibility would be really nice, right? Now, what do we know is true for this problem? Yep, but we also know that a solution exists. That's part of the projection theorem, okay? And it's unique, right? So, if I have a set of matrix equations, and there is a solution and it is unique, what do we know about this matrix? It's automatically invertible by the projection theorem, okay? So, G of y1, G of yk equals determinant of the is called the Gram determinant. And G is called, I don't know. Gram is more than 100 years old, so we can use lowercase, but let's give him an uppercase. Gram matrix, okay? So in fact, we already know y1 to yk linearly independent yields the Gram determinant is not equal to 0. Proof from projection theorem and uniqueness. Okay. Full drawn out every, how do you spell gory? Is there a Y? An E? I forget. Every gory detail is given at the end of the lecture. Do not need to know it, okay? Bingo. So we already know it's true. By the projection theorem, there exists a solution and it's unique. We just went through and showed that that solution is characterized by G transpose alpha equals beta, hence G, which is symmetric, its determinant is non-zero. So, okay, so this is how we solve least squares problems. This solves all finite dimensional least squares problems. It's a set of simultaneous equations, just matrices. Can we have a little bit of an ooh and an ah for that, okay? Come on. Ooh, ah, okay, good, good. I got that on film, okay? No, it's super, super amazing, okay? Okay, so this is our projection theorem. X minus x hat orthogonal to M is equivalent now to G transpose alpha equals beta, and x hat is alpha 1 times the basis elements for y, alpha 2, okay? So this is how you solve all minimum distance problems. You just, if you're in a function space, this is an integral. If these are matrices, this is a trace. If you're in Rn, this is x transpose y, okay? That's all you do. They're all the same, yes?
So all you need for all of these things to hold is that you have inner product space and basis subspace of that.
And x is finite dimensional. Yeah, that's all you need. This is the solution to all of them, every single one. So something really cool that we will do a little bit later on, we will deal with random variables, okay? And we want a best approximation of a random variable given an observation. Our inner product will be an expectation, as if it'll be the mean, okay? In that case, the norm becomes the variance when the mean is 0. The norm induced by the inner product will be the variance of the random variable, and we will design minimum variance estimators. It's all there, okay? They're all the same. It doesn't matter. That's all I want you to really, really get out of this. All finite dimensional optimization problems with sum of squares type norms. That's it. Okay, so let's go back to our overdetermined equations and make sure that that answer is right. Okay, so we had A is n rows, m columns, a real matrix. B was in Rn, alpha Rm. Okay. We tried to solve, and this is how we were doing it. We thought we were optimizing over the x in the equation. So we wrote this as alpha hat is arg min over all potential solutions of A alpha minus B, and this was the 2 norm. Okay, and we had the 2 norm squared. You guys remember that? Okay. And then I told you, hey, you just multiply by A transpose on both sides of this. If the columns of A are linearly independent, then A transpose A is invertible, and you just solve for alpha, done, okay? And by magic, we had alpha hat is A transpose A inverse A transpose B when the rank of A was equal to the number of columns, okay? So that's what you guys used in homework this week. Everybody was super happy. Okay, we're good? Now, let's write A in terms of its columns. Partitioned matrices. A times alpha is just alpha 1 times A1, alpha 2 times A2, plus alpha m times AM. Okay? So, we focused on finding these coefficients. We focused on finding the coefficients, okay? We weren't thinking about really what vectors are we using to do the approximation, and we weren't really thinking what is the inner product on the vector space in which those things live. But what should we really have been doing is, well, It's more apparent actually here. Here's a vector B. We're seeking to find the best approximation of this vector by the columns of A. Question?
Sorry, we assume that n is greater than But do we need to have an over-determined system?
Well, we're getting there. We have the rank of A is equal to M. So can we have n less than M? No. So it has to be at least equal. And if it's exactly equal, it's kind of trivial. There's only one solution. Okay? So it follows from this that n is bigger than or equal to M. We made all of that even more explicit than this when we set up the original problem. Okay, so what I want to emphasize here is we really didn't approach the problem from fundamentals, because what we have here is we're trying to find the best approximation of B, the right-hand side of the equation, by the column span of A. So that's where we need to set up the problem. So the real problem formulation. Question?
So the column space of A will be our M from above?
Yep. So we're going to take X equals Rn. The field will be the reals. The inner product of two vectors here will just be X transpose Y. Okay, so the induced 2 norm is the Euclidean norm. M is going to be the span of the columns of A. Okay. And we seek X hat, an element of M, such that the 2 norm of X hat minus B is minimized. Okay? So it's the 2 norm that follows from this inner product. Okay? So X hat is argmin M an element of M, norm of B minus M. Okay? So this is our X that we had always as a point in the vector space X. Okay. So by the normal equations, what do we get? We get X hat is alpha 1, A1, alpha 2, A2, alpha M, AM. And we have G transpose alpha equals beta. Gij is the inner product of AI and AJ, and beta I is the inner product of X, which is B, with AI. Okay, so just writing down the normal equations. Once we know what we're really trying to do, M is spanned by the columns of A, that's the basis. A has rank M, so the columns are linearly independent. These are a basis for M. We're trying to approximate B by something in the column span. Here it is. And so all we got to do now is figure out what does G transpose look like and what does beta look like. Okay, so Gij inner product Ai Aj, that's Ai transpose times Aj. So what would be the Ij entry of the matrix that we get by transposing A times itself? Okay, let's just write that down. So this would be A1 transpose, A2 transpose, AK transpose, that's the A transpose, and we know A in terms of its columns. Okay. Ij entry of that. Now, do you guys remember homework 1? No, it's way too long ago. Okay, so what is the Ij entry of this matrix? It's the ith row of this matrix times the jth column of this matrix. It's this, okay? Homework 1, yay! Okay, so that's Ai transpose Aj, which equals inner product. Okay, so Gij, so G transpose equals A transpose A. Okay, so we're just working out what is the Gram matrix? G is symmetric because I transpose this, I get A transpose A. So that transpose, if you don't like it, just throw it away. Everybody agree with the Gram matrix now? When I do A transpose times A, you don't think about doing an inner product, but you are. You're taking the inner product of all of the columns with themselves and just building up the Gram matrix. A transpose A is the Gram matrix. Now, what about beta? Whoops, beta I. So that was inner product of our X, which was B, with the ith basis vector. So that's B transpose times AI. This is a scalar, okay? So I can transpose it. So it's AI transpose times B. Okay, so the normal equations, G transpose alpha equals beta. That's A transpose A times alpha equals A transpose times B. Okay? Beta 1 is A1 transpose times B. Beta 2 is A2 transpose times B. So that's this equation. Okay? The columns of A are linearly independent. This is the Gram matrix. It's invertible, so there's alpha. Alpha equals A transpose A inverse A transpose B. Yay! Okay, that deserves a happy face, okay? Come on. That deserves a happy face. Okay, so you guys are playing around with just doing fits of simple functions in Rn, but we will take this, okay, let you write that. We're going to take the same theory. Each case we will simply evaluate what is the Gram matrix, what is the right-hand side, and then we'll have the answer to our approximation problems. We've got a lot of work to do now to exploit this formula. As soon as we know the vectors, as soon as we know an inner product, as soon as we know in a set of approximating vectors given by a subspace, we can find the one that's closest to the vector that we have. So that's estimation. Least squares estimation. All of those problems, each time when they change the inner product, it's different calculations to get the Gram matrix, but it's the same equations, the normal equations. The normal equations. This is what's fundamental. G transpose alpha equals beta. In each case, you work out the Gram matrix, you work out the right-hand side, you get your alpha, and then you use that and the basis vectors that you use to compute the Gram matrix, and you get your optimal X. Question?
Are there ways to show that, like, similarly, that there is, like, optimal thing for if M is not a subspace? Is there, I mean, obviously it's harder, but is it possible?
Let's see, I don't know if I quite got all of that. So here we're assuming that the rank of A is equal to M, so the columns are linearly independent. If the columns are not linearly independent, what we would need to do is to build a basis for the column span. And then the answer would not be unique because I could use different columns to get the same. It would look differently, but it would be the same approximation error. Yeah. Okay. So if the columns of A were not linearly independent, what I would do is just remove the dependent columns and rewrite the problem. That's all I would do. But, okay. Everybody put a smiley face in their notes, and no smiley face. No smiley face. Oh, come on. Throw me a bone, okay?
I don't even have the notes down.
Oh, his smiley face is right here. Okay, so good. Okay, I know.
It's very clean, though.
Thank you. Anyway, that's a grizzle smile. A little. Okay, let's spend the last minutes on something conceptually really beautiful. The orthogonal projection operator. Okay. Whoops, didn't change. That's okay. X finite dimensional vector space. Actually, inner product space. And we have some subspace of it. Okay, so if we take some point in X and we have some approximating vector in M, we know TFAE. Remember, the following are equivalent. I'm going to write down A and a B and a C. Each one implies the other. Okay. A. X hat equals arg min m and m norm x minus m. Okay? X hat is the solution to our best approximation problem. B. It's characterized by its orthogonal to m. So the approximation error, x minus x hat, is orthogonal to m. That formula is equivalent to this one by the projection theorem. C. There exists x tilde in the orthogonal complement of m such that x equals x hat plus x tilde. Okay, so remember we have our inner product space is m direct sum, m orthogonal complement, m perp. So that's what this comes from. Those are all the same statements. Okay, so I'm going to use that to define an operator. Ooh, definition. P takes x to m by P of x equals x hat where x hat satisfies any one of A, B, or C. Now, since they're all equivalent, it means if it satisfies any one, it satisfies all of them, okay? Is called the orthogonal projection of x onto m. Okay. Two exercises for you. A. P takes x to m is a linear operator. Okay, this is an amazing property. It only holds in norms coming from inner products, okay? The key thing is conceptually, P maps X to the solution of your best approximation problem. If I have an X1 and I solve the problem, and I have an X2 and I solve the problem, and my X is now the sum of X1 and X2, I get the sum of the two best approximation problems. That is not a generic property of optimization, okay? Normally optimization is extremely nonlinear. So this is an amazing statement that the solution of our best approximation problem is linear in what we are optimizing. We double this, we double the best approximation. We have x plus y. Their best approximation is the best approximation of x and y. So hint, use part C to show this. Exercises. B. Now, if you do B first, then A becomes trivial. So that's another way to do it. But let V1 to VK be an orthonormal basis. Whoops, come on. For M. Okay. Then P of x is this, sum I equals 1 to k, inner product of x with vi times vi. It's that's the answer. Do the exercise, but let's look at the normal equations. Sorry, let me let you write that down. Apologize. Inner product of x with the ith orthonormal basis vector times the ith one, okay? That's it. This makes linearity clear, because P of x plus y is inner product x plus y, and you have linearity on the left-hand side, okay? So if you do that, if you do B first, then A is evident, okay? But just look at the normal equations, okay? There it is. Suppose I build the Gram matrix out of an orthonormal matrix, an orthonormal basis for M. What is the Gram matrix then? These guys, suppose they're orthonormal. So when I is not equal to j, I get 0. And when I is equal to j, I get 1. Okay? So then the Gram matrix is just the identity. Oh, okay? If you choose an orthonormal basis, now how would you come up with an orthonormal basis? Gram-Schmidt. Or you took a course in electrical engineering and you studied Fourier series. And you learned about sine and cosine forming an orthonormal basis. And you wanted to take a function and write down its best approximation in terms of least squares, in terms of an expansion, in terms of sine and cosine. Go look at the formulas. They're exactly calculating the orthogonal projection operator, okay? These are your sine and cosine, and these are the integrals f against the sine and cosines to get the Fourier coefficients, okay? That's all it is. So everything you did as an undergrad on Fourier series, etc., you were just doing orthogonal projections. Now there, if you did the infinite series, you actually worked in a Hilbert space. I did a Hilbert space, okay, as an undergrad. but you were just solving these types of equations, okay? You're just taking advantage of the fact that when it's orthonormal, these coefficients give you now x hat. This is x hat equals p of x, your best approximation. Nobody's jumping up and down and going, okay. Anyway, that's it for today. But I hope this is starting to put a whole bunch of things together. You've seen maybe even younger days and stuff. So do not show up on your robotics qualifying exam with this formula saying that's all I need to pass, okay? You need this formula and to understand how you calculate that, and the professors will give you a situation. As soon as you set it up and you get halfway through, they say, fine, fine. You know what? You don't have to do anything more, okay? And I'll feel really good for you. Thank you. See you next week.